going to talk about the shell method. It is another way to find a volume of rotation. Have there been instances where we've said, this would be gross to integrate?
Yeah.
Or, wow, I don't know how to integrate this.
Yeah.
Okay. Here is another way we can do a volume of rotation that maybe will lend itself to sometimes an easier integration, sometimes maybe not. Okay? It's nice to have options, isn't it?
Yeah.
Okay. So when we use the disc and washer method, our rectangles were always perpendicular to the axis of rotation. If you go, if you look at these rectangles, notice how when we rotate them to get our washers, they were perpendicular to our axis of rotation. Okay, so I'm going to give you this funny word, perpendicular. Okay, today we're going to talk about the shell method. Okay, so perpendicular, perpenwascular, that's really not fun. But you know that the disc and washer method are the same, right? So if you need this funny word to help you remember, okay, please take a hold of it and remember it, okay? If you're better at visualizing, then you can draw in your rectangle and visualize, this is going to make a disc. This is going to make a washer, okay? Okay, so today we're going to do the shell method. Our rectangles will be parallel or parallel to our axis of rotation, okay? So you see we have this rectangle, and I'm going to rotate it around the y-axis, so you see I have a shell, if you will, okay? So we're going to take our area, we're going to cut it into infinitely many, infinitely small rectangles, and when we rotate all of those around, we get all of these shells inside of each other. And what can you visualize that looks like this?
A washer.
A washer?
Yeah.
Like a tree bark.
Okay, like a tree bark.
No.
A roll of toilet paper, right?
Yeah.
A bunch of shells stacked together, right? Okay. So what we're going to do is we're going to find the volume of each of these shells, right? And add them together. Okay. So if you think of this, okay, we have this shell that's basically, I don't know, we have a cylinder with a big hole, right? Where our shell is really, really thin, right? Because we cut all of our rectangles, gosh darn it. Our rectangles are really, really thin that we're twisting around, okay? So I want you to imagine this shell, and we're going to cut it and lay it out in the rectangle, okay? Yes, okay? So I want to find the volume of this sheet that the shell that I cut and laid out, okay? So we took a shell, that's laying there, okay? So this is representing, this represents where it's twisted around. So this is the circumference of the circle right there. You picture that? Okay. This is the height of our cylinder, or our shell. And then we have our thickness, right? How would we find the volume of this blue prism?
Circumference times width times height.
Okay, so essentially length times width times height, right? But our length is the circumference of our circle. So the volume of this shell is 2 pi r circumference, right? Times the height times the width. Now, what is the width of each of these?
D1.
It depends, right? In our last picture, it was
DX.
dx because the thickness was along the x-axis, right? Okay. So, okay, what I'm going to write, when we add up all of these, okay, we're going to have the integral of 2 pi r/h, basically, right? So let's go to this nice picture here, okay? Oh man, we have a lot going on there. Okay, so we have 2 pi r/h, right? And we're going to add all of these shells together. So the width we've decided was either our dy or dx. Right now, let's call it dx. Okay, so here's the width of that shell, right? 2 pi r. Here, can you see my shell? Okay. What can we describe as the radius of our shell? You're getting ahead of yourself. Okay. Our radius is just x.
X.
Okay. Any given distance is going to be x. Okay. Because I wish this was easier to go back. Okay. So we're breaking it up into rectangles, right?
Yeah.
Okay. So this is x away, at any given x, right? We're just x away with each of these. Okay. Because if we're at 2, we're 2 away from our axis of rotation. If we're 3, we're 3 away from our axis of rotation. So we're calling it x because we have all of these rectangles at different places. Okay? So our radius is x, and then the height is going to be, okay, the height of our rectangles, right? Top function minus bottom function. Okay? So here is our 2 pi r/h times the thickness, and then we are adding up all of these infinitely small shells, so we're integrating from A to B. Okay, here is our parashell method. Did you write it down? Okay. And then here's a nice little picture for you so you can imagine those shells being formed.
So doing this, is this the same as the other method just using?
Yes.
Okay, yes. If I can take a region and rotate it about an axis and use 2 different methods to get the same answer. One may be easier than the other, right? But we can still get the same answer. Okay, and we'll actually take a day and look at doing both ways, but right now I really want to focus on the shell method. Okay, Tuesday we're going to spend looking, not Tuesday, Monday we'll spend looking at both methods. Okay, but this is that region that we started with all of our shells. Okay, that's pretty sweet, right?
Did you set up all those little?
Huh?
All the little diagram things, you set those up?
I can't take credit for these.
Oh.
I found they were given to me.
No, you took
Okay.
those.
I rough, right? I went to what you may call it calculus camp before I started teaching calculus, and we got, we shared resources. Okay. So,
Oh, this one's cool.
all right. So this is what we've been looking at, right? Now we're actually going to find its volume. Okay, this is the region that we started with. So what it is, y equals 1/2 x, y equals x minus 1, the quantity squared, and we are revolving it about the y-axis. okay? So, let's get our picture. Okay, I know I have this picture here, but let's get a better picture, right? So 1/2 x up 1 over 2, right? X minus 1, the quantity squared, is a parabola where our vertex is where?
1, 0.
Right there. Right? And then it's going to go through where?
1, 1.
What?
2, 1.
Like this, right? Okay. So, I'm going to erase all these other lines so we can really see what's going on here. And we are rotating this about the y-axis, right? So we are going to rotate this until we get, and then let's like this. Okay. So since we are using the shell method, I am going to draw vertical rectangles that have thickness dx, because when I rotate long rectangles around the axis, I'm going to get shells, right? Because everyone visualize that, right? Okay. We'll worry about the intersections later here. So what I want you to remember is 2 pi r h. If you can remember 2 pi r h, you can remember the shell method. Okay, so we have 2 pi integral our radius. How far are all of our rectangles from the axis of rotation?
X.
Any given rectangle is going to be x away from our axis of rotation. Do you agree?
Yeah.
Okay. Times the height. What is the height of each of these rectangles? Okay. Top function minus bottom function, right? So our top function is 1/2 x minus our bottom function, which would be x minus 1, the quantity squared. Dx is that thickness. That's creating that third dimension. So now we're taking volume. Okay. What are our limits of integration? What are the intersections?
Well, the top one is 2.
Top one is 2.
Bottom one is
The minimum of that.
It's between 1 and 0.
It's between 0 and 1.
How about 1/2?
What do you think? Is it 1/2?
Uh,
How could we check to see if it is 1/2?
Our system is
What's 1/2 times 1/2? Okay. What's 1/2 minus 1 squared?
1/4.
Oh, so is that the intersection point?
Yeah. I said that with confidence.
I'm gonna guess.
But it was a total guess. I was trying to guess. I just figured.
How would we do it algebraically?
You set it equal to each other.
oh, that's contribution.
But then
So you would have 1/2 x would equal x squared minus 2x plus 1, right?
Yeah.
Wrong.
Yeah, x squared minus 3 times x plus 1. And then you shut up.
And then you would have to factor that, right?
And that equals 1/4. I just did that in my head.
What equals
Or 1/2 this way.
Okay.
Possible to take in your head. And
Okay, so what I'd like you to do, get out your calculator, and I would like you to put this integral in without the pi, because I want our answer to be in terms of pi.
You want us to put it to
If you
Huh?
want enough time,
Yeah, the 2 is fine, yes. We'll multiply by the pi later. 45/37.
Seconds.
Oh. You're gonna say that's a weird denominator.
Wait, no.
Do we agree with Caleb? Caleb, did you just say that?
Yeah.
Okay. Now I want you to look at our picture, which I realize isn't fabulous because I have this giant rotating area here. If we put in horizontal rectangles, how many integrals would we need? 2, because our right function, our left function changes, right? And so in this case, the shell method is extremely ideal because we don't have to break our area up. Okay? Advantage of what?
I got lost.
Okay, if I try to put horizontal rectangles in here, right minus left, it changes.
Oh,
So we
I
have, okay,
I know what you're talking
okay. Let's look at another problem. The volume bounded by y equals 0, y equals the sine of x, from 0 to pi is revolved around the y-axis. So y equals 0, x equals 0, y equals the sine of x.
Oh, I don't like sine.
Sine goes through 0.
Yeah.
And it goes
And then and it goes up,
Yep.
and it hits the x-axis at, oh, convenient. 0 to pi is what we wanted, right? Okay. So we're going to rotate this around the,
Y-axis.
how high does it go?
1.
1. So we get kind of a bundt cake without a hole, maybe?
Angel, yeah.
Yeah.
Angel food cake still has a hole. Yeah. In the middle.
Okay, but
Okay.
it's cold.
It's like a donut.
Without a hole. Okay.
Like a bagel.
Okay, so if I'm going to rotate this around the y-axis with shells, I would need vertical rectangles with thickness dx because then we would create a shell around the y-axis. Can you visualize it?
Yes.
Then we get these shells. Okay. So our volume. 2 pi r. Our radius, how far are each of these rectangles from the x-axis? These are all x away from the y-axis, excuse me. 2 pi r h. What is the height of every rectangle?
1. Oh shoot, no, it's sine of x.
Okay, top function is sine of x, bottom function is 0. So sine of x. dx, that's the width of all of our shells, okay? Our limits of integration would be from
0 to pi.
0 to pi. Okay, now this is something you definitely cannot integrate by hand. Those of you who go on to take Calculus 2, you will learn a method called integration by parts where you can integrate this by hand, but right now you do not know how to, so you have to use your calculator.
Too much fun. It's some kind of fun juniors.
Some of your seniors will be taking calculus.
People with big problems. They really don't know how to want to do stuff.
Okay. Now, if you approximate this without the pi and you don't get a nice fraction, do not put 17.345 pi. If it's a decimal, multiply it by pi. Don't write a decimal times pi. That's ugly. Okay.
Well, we answered 2 pi pi.
It's 2 pi pi.
So 2 pi squared.
Bam!
Nice.
Oh, so fun.
Well, that's kind of cool.
We're gonna look at the area.
But what does it approximate to be?
19.79.
0.79. 7.
739.
You are sassy today, Caleb.
Jeez.
Okay. Ooh, changing the game here a little bit. We're gonna rotate about the x-axis. Okay.
Because we need them to be shell. And talk to be rotated about like
No.
lines. You can know.
Okay. So y equals 4x and y equals x squared. Where would these two meet?
0, 0.
Okay.
Yes.
Where else?
2.
Where is 4x equal to x squared?
4. Definitely not. Yeah, 4. Duh.
4?
Yeah.
4 what?
4 1.
Or 0.
16.
4, 0. 0, 4.
Duh.
That was a rough one. Okay. So now, if we want to twist this or rotate around the x-axis, meaning we would get something that looks like this, right? Okay.
It's like a gun.
Okay, what I want you to imagine, if we have vertical rectangles, we would be getting these washers, right? Can you envision that? Okay, if we have horizontal, then we get these shells. Okay, what's the thickness of each of those little rectangles? dy, which means we're integrating with respect to y. Does that change anything else about our problem?
How you plug into the integral, doesn't it?
Okay, we will need to do that.
Okay.
Okay. But as far as 2 pi r h times the width, does that change?
No.
That does not change. So 2 pi r, what's the radius? How far are all of these from my axis of rotation?
Why?
They're all y from the x-axis, right? We need the height of those rectangles. So right minus left. Okay, now we have to do a little bit of algebra, don't we? Y equals x squared. This is just x equals, okay, x equals square root of y. And y equals 4x, that's x equals
Y over 4.
y over 4. So when we say the height of our shells, right minus left would be radical y minus y over 4 dy. Our limits of integration would be
0 and 4.
0 to 16.
0 to 16. Okay. Now, we're not going to integrate this by hand, but would this be terrible?
Yes. All terrible.
This would not be terrible.
No, it wouldn't.
This would not be bad at all. Okay? I'll let you go ahead and use your calculator, though. Leave out the pi. We'll put in the pi later.
It doesn't matter.
It doesn't matter.
It doesn't have a big fraction.
2048 over 15.
That's a fraction.
Yeah.
Beautiful, isn't it?
Well, see, there's a thing when I put it into a fraction. It didn't come out It's still.
Don't you hate that? Just when something doesn't work and you try to enforce.
Okay, hold on. Let me get my. There we go.